Morning, everyone. Today we are going to talk about optimization in relative scale. The problem we are interested in is similar as before. We want to minimize f of x over a closed convex set Q. Here we also assume f is closed convex. In the smooth setting, we usually assume the function f is L smooth, which means the gradient is L Lipschitz continuous. But this is a universal number. So this L is for any pair of x and y in the set of Q. And sometimes we also assume strong convexity. When we say f is mu strongly convex, then we mean that the function value minus its linearization at a certain point is at least a quadratic function. It's overbounded by quadratic function. And this is also a global condition for any pair x and y in set of Q. So these two sometimes are a little bit more restrictive than some local conditions because we need to assume the existence of these two global constants, L and mu. But in many cases, in real applications, they do not really exist. For example, there's an interesting application called the optimal design in statistics. In the optimal design, we want to minimize the function f of x. Here, x is still a vector in Rn. We want to minimize f of x, and this f of x is the negative log determinant of a matrix. This matrix is H times capital X times H transpose. H is some given data. It's a matrix. So here, H is in m by n, and the rank is m. And we assume n is at least m plus 1. And here this capital X is a matrix. It's just a diagonal matrix, and all the elements on the diagonal, it's just the elements of the vector x, right? So this is a diagonalized vector of the little x. And x here, the Q set means the simple x. So this is a unit simple x that we used in mirror descent, right? This just means a set of x in Rn such that all the elements of x sum to 1 and x is in the negative orthant. Okay, so in this case, you can try to upper bound this quantity. Well, you will see there is no universal constant, no global constant L that is suitable for any pair of x and y in the simple x. Well, in this case, we may need to resort to a new notion called relative smooth and relative strongly convex. So the intuition comes from here, because here this is with respect to L2 norm, right? Both this norm and this norm is in L2 norm, and here it's also in L2 norm. Recall what we have seen in the mirror descent lecture. We defined the Bregman divergence. So this is for a function h, and we call the function h as a distance generating function. Bregman divergence is defined as follows. So for a function h, we call the Bregman divergence of h between 2 points at x and y as h minus its linearization, right? This is just a linearization at the point x, at the point y evaluated at the point x. So this is and if h is one half times L2 norm square, then the Bregman divergence for h between x and y is again a Euclidean distance. Right. And this is equivalent to rewrite this inequality in terms of this one, in the same format as this one. So we have f of y right. So here it's actually the Bregman divergence of this h between x and y. There's no one half, just L. Right, and here it's also, we can rewrite it in terms of this Bregman divergence. Right, this is a way to generalize it a little bit. Using this Euclidean distance, we can rewrite this Euclidean distance as the Bregman divergence of this function h, and here's also function h. So then, so from these two inequalities, we may generalize smoothness and strong convexity using Bregman divergence. So we could define relative smoothness and relative strong convexity. For Euclidean distance, it's okay to exchange x and y, but in general, this should be y with respect to x. Because the Bregman divergence is not symmetric. It's not a real distance, it's still asymmetric, so it's a divergence. So maybe we may generalize this sandwich inequality in this way using the Bregman divergence for general distance generating function h. And when h is the Euclidean distance, we still recover the normal notion of smoothness and strong convexity. Okay, so this is going to be our formal definition. So this is a definition for strong convexity. This is definition for smoothness in the relative scale. That's why we call it optimization in relative scale, because now everything is in terms of the function h, and we call h as the reference function. What differs from One difference about the function h, this generating function h in this lecture and the one in the pure design lecture is that in the other lecture we usually assume the function h is strongly convex, but here we do not assume h is strongly convex. For the case when in that lecture we assume h is mu strongly convex in the normal sense using L2 distance. Then you can show that right, because the Brockham divergence is again in this format, function h minus its linearization, right? So if h is mu strongly convex, then we still have this left-hand side inequality. That's the case in mirror design, but here we do not assume h is strongly convex in any sense. And here, if both f and h are twice differentiable, meaning that the Hessian exists, then we also have, so suppose both the hash of h and f exist, then we can rewrite this inequality in terms of the Hessians. This is in the for nx in the interior of Q. for relative smoothness, we have the following equivalent statements. First, when we say f is L smooth relative to H, then it's equivalent to say LH minus f is convex on Q. This is the technique that we have used to show many equivalent statements about smoothness, the normal smoothness. And it's also when both f and h are twice differentiable, it's also equivalent to say this inequality here. And it's also equivalent to say this inner product is less than or equal to L times this inner product for any higher x and y in the interior of Q. The reason why we usually have interior of Q, for example, similar to this setup. So the function f is usually non-differentiable on the boundary, or sometimes, for this case, it's on the relative boundary. For example, when we talk about minimizing the relative entropy or the negative entropy, when we minimize the negative entropy over the simplex, recall from one of the problem sets, we do need to assume h is in the interior of delta n because on the boundary, it's not differentiable. So here is also the same case. When we talk about differentiability, we usually use the interior of the set Q. These four equivalent statements are easy to show using, just use this function. So call this function as another function phi, then you can show these are all equivalent. And using similar ideas that we use to show equivalent statements about smoothness in the normal setting. I will leave this one for a homework problem. Okay. And we also have a corresponding lemma for equivalent statements about mu strong convexity in the relative sense. Similarly, we also have the following four statements that are all equivalent about the mu surrounding convexity in the relative sense. And this one is just symmetric of this one, and you can similarly show this one using these four equivalent statements. Okay, I will skip both of them. And in the homework, I think you just need to show this one. You can skip this one. Let's consider this example. Suppose the function f is twice differentiable and convex on Rn. Rn is going to be the Q. Suppose the operator norm, which is L2 norm for the grid for the Hessian of f, is at most this much in terms of the L2 norm of x. This is a vector norm. This is a PR is a polynomial, the R degree polynomial. And also we assume, let's set the function h, the reference function h, to be this one. It's this is L2 norm, but to the power R plus 2. This is again L2 norm to the power 2. And let's set this constant R, this constant L, the smoothness, to be an L such that for any alpha that is non-negative, the polynomial of R is at most L times 1 plus alpha to the power R. And then for this pair, this L and this reference function h, we can show that L is indeed L smooth relative to this h. So to show this one, because we have twice differentiability for both function f and also for this one here, you can check this h is actually twice differentiable. So because both of the two functions are twice differentiable, we are going to use this equivalent condition to show f is smooth relative to h. Okay, so because h is explicit to us, let's try to compute the Hessian of h. We first compute gradient. So for this one, we first compute the gradient of h. So here, taking the gradient of the first term, we will have this term here is because we need to use the chain rule to compute the gradient of L2 norm. Right, this is just the gradient of this one, right? This part. So canceling one factor of x2 norm, we will have this one, and then taking the Hessian of the, so taking gradient again to this, taking the Jacobian to this one again, we get the Hessian, and after simplification, we get this formulation, and because this is a positive semi-definite matrix, So this is superior to this one, and this is also superior to this one because of this condition here. For any non-negative alpha, we have this condition, and here the alpha is just the L2 norm of x, right? Which is also non-negative. And the last term is because the last inequality is because this condition, right? This is bounding the largest eigenvalue of the Hessian. So from here we can see we really verify this condition, hence the claim is true. F is relative, L smooth relative to the function h. And we can do another example for the d-optimal design problem. The function f is, as what we mentioned before, it's the negative log determinant of certain matrix. And here this is capital X, which is just a diagonal matrix. The diagonal elements are the elements in the vector X. And Q is the simplex, the unit simplex. We define H to be this function. It's negative summation log of each coordinate xi. And the claim is f is just a one smooth relative to this function H. Here, because both f and h are twice differentiable, so we again use this. We still check this condition. We compute the Hessian of h, Hessian of f. I will skip the computation for the gradient at Hessian of f, but you can check it using matrix calculus. So here the gradient of f is the negative diagonal of a certain matrix C. C is defined in this format. And we also have the Hessian of f. The Hessian of f is C Hadamard product with C. This just means the ij element right? The element on the S row and the J's column of the Hessian is just the Cij times Cij. Okay. So it's just an element-wise product between the same matrix. Let's call this matrix U to be H times 1/2 x. 1/2 x exists because x is in. So here we are just taking the square root of each xi and put it on the diagonal. It exists because x is at least 0, right? X is non-negative, so we can take the square root. And then we can show, actually this condition holds in general for any matrix U as long as this matrix is invertible. This is true because this is actually a projection operator. So suppose I want to solve, suppose I have a vector. This is a vector P. Right, and then I want to do a projection onto this space. So I do this decomposition, right? This is the vector on the space, and this is the vector orthogonal to the space. So to solve what this vector is, so this is my space, right? U transpose X equals some constant C. This is my linear space. And to do the projection onto this space, I need to solve this equation, right? I need to find the projection onto this space. So solving this one, so let's multiply U on both sides. Left multiply U on both sides. Right, and assuming U times U transpose is invertible, so we find this X to be U transpose inverse U times P. And the vector on this space is U transpose times this X. Right, this is the vector on this space. So this vector here is actually U transpose times X. And then let's see why we have that condition about the matrix. So to show that one is equivalent to show U minus U transpose U is to show this one is positive semi-definite, right? So the way to show this is positive semi-definite is by showing that for NAP, if you do this multiplication, right, if you can show this is true, show this quadratic form is negative, then we can show this one, right, for NAP. And let's use the definition here. So this part U time, so this matrix multiply on U is this part, right? This matrix multiply on U. This is the projection onto the space. So we multiply U in P inside, this is P minus U transpose X. Right. And pictorially what this is just the vector that is orthogonal to the space, right? Maybe let's call it P orthogonal. So this is just the P inner product with P orthogonal. And from the picture, we can see this inner product has an acute angle, right? Because the two vectors has an acute angle. So this is at least 0. This is always non-negative. So we show this is really non-negative for any P. And hence, this inequality about the matrix is true. Okay. So here we're just doing a projection. So this is true for any U as long as this is invertible. And hence, it also applies to a specific U that we define as H times 1/2 Hx. Okay, so now let's use, let's plug in the value for U. Then we have right here, we just plug in the value for U. And then let's multiply x negative 1/2 to the left and also x negative 1/2 to the right. Right, then we have this inequality about the matrix. And from this definition, this is just the matrix C, right? This means C, oh, sorry. Here, this is X inverse, because it's the square of this one. So we have C Okay, now let's check the condition about the hashing. Because here we say the hashing of F is C Hartmann product with C again. And using this inequality and the fact that, so the conclusion here is C X inverse Okay, so from this conclusion, we can say that F is 1 smooth relative to H, right? Because here the L is just 1. So this is by the computation. We have the format of hashing of F. And this is because of the inequality that we just arrived at. And another fact that, so this can be rewritten as C Hartmann product with C minus, let's write it in another way. This is equivalent to say C X inverse minus C. This is a positive semi-definite matrix. And the reason why this is true is because here C is a positive semi-definite matrix. And this difference, X inverse minus C, is again a semi-definite matrix, right? Positive semi-definite. So this is because this conclusion. And this is a Hartmann product with about two positive semi-definite matrices. And there is a claim saying that the Hartmann product of two positive semi-definite matrices is again a positive semi-definite matrix. So this is true. And this inequality is because of the same reason. So we can do the same factorization as x inverse minus c Hadamard product with x inverse. Right, because this is again positive semi-definite, x inverse is also positive semi-definite, right? Because each element on the diagonal is just a 1 over xi. Right? So it's also positive semi-definite. So we have all these are true. This is because we are basically doing element-wise product. So for the ith diagonal element is just the xi 1 over xi. So basically we are taking the square, right? So this is just this is the ith element of this matrix on the diagonal, and this is by computation. Here we can easily show that the hashing of H is just this matrix. Okay.
YC is a positive semi-definite.
Because of this format of C.
H can be any matrix.
Yeah, if you multiply, for example, if you multiply a vector y transpose cy, so here you have y transpose h transpose. This is hy transpose. Right, this is another vector. Let's call it C. Because this is positive semi-definite. Right. This can be rewritten as so from here we just need to show this is non-negative, right? And so we just need to show this is positive semi-definite matrix, right? Ignoring the inverse here, if you can show the original one is positive, then the inverse is also positive semi-definite, right? And this one can be rewritten in a summation form. H x H transpose. This is Hi is the column, the ith column of capital H, the matrix. Because this is a positive semi-definite matrix. So, and this is non-negative. The summation is again positive semi-definite. Okay, so from here we can say F is 1 smooth relative to H. So here you can see the powerfulness of this new notion, relative smoothness, because this function is not smooth in the normal sense with respect to L2 norm. If you try to find a global smoothness parameter, well, if you use H as a reference function, then it is indeed smooth. And actually, the L is small. Whenever L is small, the guarantee in complexity is small, right? Because the complexity is proportional to L. If you do not do acceleration for smooth optimization, the convergence rate will be this much, right? So if L is small, that is good for us.
Professor, so what happens if your global optimizer or global minimizer is on the boundary? So like in this example, it won't be, but a lot of these functions aren't defined if x is equal to 0, which is technically within Q, but we're only considering the interior. What happens if it's on the boundary? Or is that just not, does that not happen in practice?
It doesn't happen very often in practice. Well, in that case, I believe the minimizer that you can obtain is very close to the boundary. So yeah, this is a good point. There is a method called the interior point method. So for example, for solving linear programming, this is your constraint. It's usually a polynomial, right, in linear programming. This is AX less than equal to B. And so the simplex method is just jumping between all the vertices, right? You just solve the solution at the vertices. But the interior point method is different. So starting from some interior point, and then you go along. So for linear programming, we know the optimal solution must be one of the vertices, right? For example, it may be this one. And then the reason why the method is called interior point because all the point that is returned by the solution, by the algorithm, the iterates, are in the interior of the domain, interior of this polyhedron. So it may go along this path. It's approaching this point, but all the search points are interior points. So you will never approach the global minimum. Well, in the end, you need to do some other techniques to approximate this point to one of the closest vertices. So that sometimes happens in algorithms, but in the end, there is some way to approximate this one to a close vertex. But you can never approach any of the vertex because the algorithm just works in the interior of the domain.
Okay, thank you. Sure.
Now let's present some algorithm for solving function that to minimize function that is L-smooth in the relative sense. Method is pretty much like what we had in the Euclidean setting. So we call it a primal gradient method with reference function h. The input is the initial point x in q, and also we need the reference function h and the L smoothness. That is so that the two satisfy the definition one. Definition one means the relative smooth definition. And then in the algorithm, the iterate is a little bit. It's just a generalization of what we have in the normal setting. Recall in the normal setting xk plus 1. Right, if we use Euclidean distance, this is the iterate for xk plus 1. And here we just generalize this 1/2 L2 norm square by this argument divergence for the function h. Right. And here's the convergence guarantee we have. Suppose this function f is both L smooth and mu surrounding convex relative to the reference function h. Then we had the following convergence guarantee. The primal gap converges exponentially fast with this rate 1 plus mu over L minus mu. This is faster. So this is because this is greater than 1. So this is geometrically fast convergence, linear convergence. The rate. So this is just a geometric sequence, and here is. Usually, what we have here is just the distance between x and x star. But here we replace the Euclidean distance by the Bregman divergence. And this is useful for the case when mu is 0. So this inequality shows that when mu is 0, then the convergence rate is 1 over k. It's just the same as what we usually have for the case where we do not do acceleration. We have 1 over k. If you accelerate, in the ideal case, it would be 1 over k squared, but I think this is still an open question for optimization in relative scale. If you are interested, you can try to solve the problem for acceleration in your project. So before we show this theorem, this convergence guarantee, we need to state a 3-point lemma. This is quite similar to what we had in the lecture for mirror descent. Recall that in mirror descent, we say there is no this phi function. This is so there's no phi of x, there's no phi of z plus. Then this is equality. But here we generalize it a little bit by putting a phi function here. This becomes an inequality. So this is saying that here is nothing about relative smoothness. This is just a general statement. Suppose phi is a convex function on Q, then I'm interested in solving this problem, phi x plus this Bregman divergence. Here z is given. I want to find the next iterate z plus. This is like xk, this is like xk plus 1. And then for nx, I have this inequality. This is like the strong convexity result we usually have. So from here to here, this is by minimality. And because of the strong convexity, we have some extra space to put another quadratic, right? That's the lemma we usually use. But here, the extra space is not for L2 norm, but it's for this Bregman divergence. We will use this lemma in the theorem, but we will skip the proof of this one. It's very simple, like what we usually have. The first inequality is because of the L smoothness. Right? This is just the definition for L smoothness with respect to the reference function h. And the second one is because of this lemma. Right here, you can view this phi function as the linearization divided by L. And then you multiply the whole thing by L, you can get this the second inequality. And the third one is because of the mu strong convexity with respect to x. Right? Because this part is the same as this one. So, and we can also cancel this L portion of the Bergman divergence, move this minus mu to the other side. This is exactly the mu strongly convexity in the relative sense. Okay, and one observation from this inequality is that because here this x is arbitrary for nx, okay, and if we take this x to be xk, then this one becomes 0, right? dh of xx, okay, this is 0. And this one is negative. So we have f of xk is a monotone, non-increasing sequence. So this is the same conclusion as what we had in the normal sense for the L smoothness. So if the function is L smooth, and then if you choose your step size lambda to be at most 1 over L, then you can guarantee every iteration will be a descent iterate. So descent is in the function value sense. Okay, then from this one, show this inequality. So here we just multiply each inequality with, suppose this is I, let's change the index, change this k to be I minus 1, right? Change the inequality, and then we multiply each inequality with this factor, with L over L minus mu to the power I, and then sum the resulting inequality from I from 1 to k. Then we get the following inequality. Here we have a telescope sum, right? Many terms will cancel out. And then we put this term to the left, and let's take x to be x star as well. From here, we can also make use of this fact. F of xk is non-increasing. So the minimum for this one is just the last term, f of xk, right? It's greater than or equal to the right? So we can also have this inequality, right? Because this is the smallest among all the f of xi. And then we rearrange the term, take x to be x star, and also ignoring this negative term, we will arrive at this inequality. And now let's divide the whole thing by this big summation. Because this is a sum of geometric sequence, then we can indeed have this bound here. This is just computation. Okay, and from here to here, this is an upper bound because if you do Taylor expansion of this term, so 1 plus L over L. Right. If you do a Taylor expansion of this one, you will have 1 plus k times this quantity here with other high order terms in terms of L over L minus mu. And this one to the power k minus 1 is exactly greater. So this is greater than or equal to 1 plus k times L over L minus mu. Oh, here's mu. Sorry, this is not L. Here's mu. So this denominator is greater than or equal to k times mu over L minus mu. And if you do the cancellation of mu, you will arrive at this inequality. Okay, so then we conclude this proof. Okay, this is everything about the primal method. Next time I will introduce a new method called dual averaging. This is not a new method in this relative scale optimization, but this also applies to the case where we have just the normal non-smooth or smooth functions. But this is also doable, just like the primal algorithm. It's also doable in the relative scale setting. So we will talk about this one next time. Okay. See you on next Tuesday.
Hey, sorry, I meant to reply to your text. I just been slammed nonstop.
That's fine. How are you?
Pretty good. How about you?
Good. Perfect. I really enjoyed your talk yesterday.
Oh, thanks.
The topic was so, exciting, and I think you've been working on it from your undergrad.
No, well, that one I kind of started working on my undergrad, and honestly, that's not even the thing I'm working on anymore. I alternate between it because that's the problem that DARPA's funding my PhD for.
Cool.